Hello. As promised in my previous video, I'm doing a couple examples with circular motion. I'm going to do two exactly. And the first one on the left there, I've already set up a little bit. It's a picture of a circle or drawing of a circle. The radius is 10 centimeters, and I give you the rate of change of velocity, aka the acceleration, dv/dt, and I gave that to you in unit vector notation. And we're going to talk about some things to determine about the circle. I also kind of rewrote basically the definition of radial acceleration, both the equation and what it means, and then also the definition of tangential acceleration. There's not really an equation for that, but I'm telling you what it means. If you need a moment, you can go ahead and pause the video and kind of copy this stuff down if you'd like, and then we'll get going. All right, so for our example here on the left, for the circle, first of all, let's assume that this is like a car, a little toy car traveling on a track, on a level table. So we're not going to worry about gravity like in the first example we did in the previous video. So everything is going to be just, here's your acceleration, 20 I hat minus 8 j hat meters per second per second. There's a couple things I want you to determine. First of all, we're going to assume that the car is at that spot in the circle, so on the west part of the circle. And we're going to determine A, what's the velocity of the car, okay? And B, is the car speeding up or slowing down, okay? Now, normally at this point in the discussion in class, I would pause for a minute. I would give the students some time to give that a shot. I encourage you to do that. I encourage you to pause the video for a sec and give that a try. But I am now going to run through how to do it. So first of all, the acceleration, I'm going to sketch the I and the j components on the diagram. So there is a component of acceleration this way, and that is 20. And there is a component of acceleration this way, and that is 8. Okay. Now, we automatically know a couple things. The one that's pointing inward, that has to be your radial acceleration, okay? And the other one, because it's perpendicular to that or tangent to the circle, this has to be your tangential acceleration, okay? So we've now figured out our radial and tangential components of our acceleration. To figure out the velocity, how fast this thing is going, we're going to use the radial acceleration equation. Radial acceleration is v squared over r. So I'll do that down here. Okay. So a sub r equals v squared divided by r. A sub r we just figured out is 20. We don't know v. And the radius is, oh, sorry about that, is 0.1. Okay. So v squared would be 2. Therefore, v would be about 1.4 or so meters per second. So not going terribly fast, but it's a really tiny circle. So there you go. Okay. Now, a quick reminder. How did I know that the 20 was the radial acceleration? Well, again, that points inward. That is your I hat direction. That's how I know. So my big hint to students on a problem like this is always draw the circle and always sketch everything you know in the circle, and that will help a great deal. Frankly, that's the only way I know how to do it, is sketch a circle and then kind of draw the directions of my accelerations and stuff, okay? Now, the last question I asked you was, is it speeding up or slowing down, okay? Well, it turns out I haven't told you enough information to answer that question, okay? If the object were moving clockwise, as I just drew, then it would be slowing down, okay? However, if the object were going counterclockwise, then it would be speeding up. In other words, if your tangential acceleration is against the motion, you're slowing down. If your tangential acceleration is with the motion, then you're speeding up. So not only do you got to know the tangential acceleration direction, but you also have to know the direction of motion in order to answer that question, okay? Now, for my second example, okay, let's do a similar one. So let's say I give you a circle. Something is traveling in a circle. And this time we don't know its radius of the circle, okay? But I give you the following data. I tell you at a moment, the acceleration, aka dv/dt, same thing, okay, is 5 meters per second at 40 degrees north of west. So you know that. And I also tell you the velocity at the moment I'm interested in is negative 20 I hat meters per second. Okay. All right. So the two questions I would like to know is, what is the radius of the circle? And is the object speeding up or slowing down? Okay, I won't write all that out, but is the object speeding up or slowing down? And what's the radius of the circle it's traveling in? Okay. Now, normally if this were a lecture, I would pause for a couple minutes and let my students kind of consider how to do this. Again, I strongly encourage you to do that. I encourage you to sketch, okay, and draw where you think things are happening. I will give a couple hints. The velocity is to the left. So there can only be two places in the circle where that's happening, okay? And secondly, I would strongly urge you to write the acceleration in unit vector notation. That will help you figure out where the object's at and then what the radius is, okay? So before you can calculate the radius and tell me if it's speeding up or slowing down, you're going to have to first figure out where in this circle that I've drawn, where is the object at, okay? Also, and another thing, it is on level ground again. There's no gravity to worry about. It's like a little car turning in a circle. All right, so give that a shot, and in a moment I'll run you through how to solve it. All right, so the first thing I would do is rewrite the acceleration in unit vector notation. So to find the horizontal component, it would be 5 cosine of 40. Okay, and if you do that, and it's to the west, so it's negative. Okay, it's left. And 5 cosine of 40 is approximately 3.83, and that would be I hat. And then the vertical component, the j hat component, the north component, would be 5 sine of 40. And if you take 5 sine of 40, you get 3.21 j hat. And again, that's north, so it's positive, it's up. And that's meters per second per second. Okay, now, because we know the object is traveling to the left, west, there's only two places it can be in the circle. It's either at the bottom of the circle moving left, or it's at the top of the circle moving left. So how do I figure out which one? Well, if the velocity is left, that means the radial acceleration has to be vertical. It has to be up or down, okay? So in my acceleration equation, the positive 3.21 j hat, that's your radial acceleration, okay? That's perpendicular to the velocity, perpendicular to the circle. Well, if I were to put that up here, that doesn't work because radial acceleration always points inward. So the object cannot be at the top of the circle. So it turns out the object's down here, and it's got a radial acceleration of our 3.21, okay? And it's got a tangential acceleration to the left of 3.83. So that's our tangential acceleration, that's 3.83. So right away, I now know that the object is speeding up because it's moving left, negative 20 I hat, and it's accelerating left. The tangential acceleration is in the same direction as the velocity, so it is speeding up, okay? Now, what about the radius of the path? Okay, well, I'm going to use my radial acceleration equation. AR is v squared over r, okay? A common mistake that students will make is they'll put a 5 in for radial acceleration, but that's not the radial acceleration. The radial acceleration is only 3.21. So if I sub in 3.21 equals v squared, which is 20, so 20 squared divided by radius. So, you know, you can do your math. You're going to do 400 divided by 3.21. And you get a radius of approximately 125 meters. So this could be like a car turning in a parking lot, for instance. And 20 meters per second, that would be about 44 miles an hour. So that would be something feasible to do. Okay. All right. So again, big hints on these. Make sure that you draw the path. You figure out where the object is. You draw the accelerations in. This helps so much when you draw stuff out. Our brains are wired to see pictures. So drawing a picture here will definitely help you considerably. Hope that was helpful, and thank you very much.